He changed.
For some reason, Sterling says that. With the functional events.
Do you want to focus on?
I will do the rest.
Yeah, my understanding is it won't work if you do single point.
Probably.
Okay, so our main goal is to be in time because some of you have plans for lunch or other courses. The goal of this course is physical chemistry to predict outcome of measurements and predict future of the systems, different physical systems, chemical systems that we need to characterize. And in the course, we do have some background of quantum theory without which one cannot go forward. The equations are so complicated, as you have experienced from how it works, that one needs some additional numerical tools. So today we are going through the fundamental elements of the computational modeling of quantum dynamics and some aspects of practical use of the code that was considered in the course. The time for each speaker is 5 minutes, including presentation and questions. We definitely will be going a little longer, but please respect your classmates and do not go over and give chance to the audience for answering questions. If you haven't seen the Microsoft Windows before, here it is, and you find your number in the schedule and your name, click on it and go for launching the thing. So with this, I would like to announce first speaker Howlett, who will tell about operators and main principles of quantum dynamics. It will be remote.
Awesome. Thank you, Professor. All right, good morning. I'm Bill. So today we're talking about the Wavepacket propagation and the evolution, Hamiltonian, and momentum operators. For Wavepacket propagation, simply what we're looking at is the wave packet. It's just a short burst of localized wave action over time and how it travels as a unit. Essentially, the way we analyze and synthesize this is by looking how it interferes constructively or destructively. More so in this course, we have looked at it, how it interferes constructively in a small region of space and then destructively everywhere else. The profile of our packet can either be constant or it can change. If it does change, we experience dispersion, whereas if it remains constant, we experience no dispersion. Quantum mechanics seems to define the wave packet in a different sense. It seems to define the wave packet as a measure of probability of where the particle will be. And essentially, if we get the probability density of our particle, we can further derive how it accumulates phase at a particular eigenstate, and then measure that to find the momentum and the position. So when we look at wave packet propagation, simply what's happening is the wave packet is accumulating phase over time, and we're describing the behavior of the wave as it does accumulate that phase, and how that eventually correlates with energy. So kind of how we're going to outlook today is the evolution operator and how that has the Hamiltonian, how we can express it, essentially the evolution operator as the Hamiltonian, and then the Hamiltonian expresses the momentum, and then we can put all these operators into matrices to simplify our expressions, make it easier to solve and predict the future. And then we can express our momentum as a matrix of the Hamiltonian, simplify the expression further, and then eventually plug all those expressions back into the evolution operator to find the position and momentum of the particle over time. All right, so mathematical wise, this is our evolution operator in the top part. And then since we know the Schrodinger time-dependent equation, we can simply use that and our evolution operator to define and derive a way to express the evolution for a long and short trajectory. Okay, so for a sample wave affected by momentum for 3 offsets, so that's accumulation over 3 phases, we get a matrix form that looks such as this. But in reality, we can have n number of propagations or phases, so we get more so a definition of the lower right. And essentially, the reason why it is necessary to need the momentum operator is to express the Hamiltonian, which makes it a lot more simpler to define the accumulation of phase. And so in MATLAB, simply we have these two lines of code that derive the wave packet. And then this is just a graphical representation of kind of what happens over time as the wave function does accumulate phase. So time evolution of a slow particle in a free space, the position over time, just some graphical representations of what happens of the wave packet. All right, the momentum operator is an operator associated with linear momentum. Essentially just describes how the particle moves. It comes from the de Broglie plane waves. Essentially what happens is that the momentum operator produces a value that is different than the linear momentum. So operators are different than just linear values. So instead of a regular linearized value, we get an eigenvalue. Thus we will get something later called eigenenergy. When the momentum acts on the superimposed wave function, it tends to yield eigenvalues for each plane wave component. And then the new components then produced by the action can then be superimposed to form a new state. Momentum operator then can be expressed as a conjugate variable of position by the Heisenberg uncertainty principle, which explains that if we know one, its counterpart must know the other. Thus, we can commute the momentum operator. And then furthermore, we can also apply a Fourier transform of the momentum operator to produce position and vice versa. Thus, we can change our perspective from momentum to position basis. So looking at mathematics again. Again, we define the momentum operator. We can then express the momentum operator as it applies to the wave function, and then how we apply that over numerous offsets. So for this example, we have 3 offsets. We can then further show the commutation of the momentum operator and how that equals simply I times x constant. We can apply a Fourier transform to convert our momentum basis to position. And in this case, it's important to note that delta is the Dirac's delta function. And again, the main principle is that when we apply the momentum operator to the wave packet, we can define the accumulation of phase. So in MATLAB, these are our main areas of code. Moving on to the Hamiltonian operator. This one is associated with the quantum system's energy. So the Hamiltonian is the sum of the kinetic and potential energy of the wave packet. It's different for a different number of particles. When the Hamiltonian operates onto the wave function, we can either get the time-independent or dependent Schrodinger equation. This then can produce our eigenvalues for energy. When we use the time-dependent Schrodinger equation, the Hamiltonian does have a pretty significant role in that it can manifest the spatial and momentum components based off time. And then additionally, we can generate the time evolution of the wave function with the Hamiltonian when we apply it. Okay. So again, we express our Hamiltonian. We can express the Hamiltonian as a particle in a box or as a free particle. And it's good to note that here, the free particle, we can express it as momentum squared over 2 times the mass. So we can express, again, our evolution operator in terms of the Hamiltonian, and then later into a momentum. The Hamiltonian can then act on the wave function as with the momentum operator, which then can be used to solve for the wave equation to give us 2 sinusoidal waves. We can then apply the Hamiltonian into a discrete form of density of states, which can then be used to find the expectation of the wave function. So where do we expect the wave to proceed? And then we can also commute. So since we know the momentum operator, we can then define commutation of Hamiltonian. And then just kind of an added extra part with a harmonic oscillator, we can define the Hamiltonian as well. And then here are just all of the examples of code. Wherever it says ham is typically a good portion of where the Hamiltonian is met, and then mesh is kind of applying the Hamiltonian to the wave packet. So finally putting it all together, we can take the evolution operator, express it as the Hamiltonian, take a Hamiltonian, express it as momentum. We can then put all of our operators into a matrix set or in forms of matrices to simplify our expressions. And then we can plug in our Hamiltonian, which we have expressed as a matrix of momentum, plug it into our evolution operator to eventually find or predict the future in time as the wave packet propagates.
Okay, let's thank Bill. And the presentation is open for discussion. Any questions? Yes.
So your Hamiltonian is presented in the MATLAB through the matrix representation, or you solve differential equation?
So in MATLAB, we normally just use the equations, but in MATLAB you can also express Hamiltonian as a matrix as well. If you know.
But what you do for this program, because you show in the pieces of program, right? Not
Yes.
just how you can work with it. Clearly you can do either this or this. The question is what exactly is implemented into the piece of program which you are using for this wave packet dynamics.
So what we are implementing is simply just the Hamiltonian as itself. We're not really using matrices. We're just
So
using.
you're not using matrices, but you define your momentum as a matrix.
Just a second. Anyone in the class wants to object?
The Bell statement?
Yeah.
Yeah, we're using matrices, Bill.
Oh, we are? Okay.
But go back to your momentum.
Thanks for making me laugh.
Go back to the momentum operator. You are showing momentum operator, right?
Yes.
In a way, how is it was used in this one, right? So you're using it in a which form?
Matrix.
And then go back to your definition of Hamiltonian. Px, right? No, this is not definition. This is definition from, general point of view. The way how you implement it in the program. Where is the line in the program showing you how you find in the operator?
First line in this slide.
Ham. This is what you just told, right? You said like, oh, where we call in a program ham, it means Hamiltonian, which we define through top line, right?
Yes.
So look on it and tell me then, how is it defined through what you need to define it. There is px, right? I cannot really see it.
POP.
POP.
That's supposed to be the momentum.
Huh?
So Hamiltonian can also be momentum squared over 2 times the mass.
So, and momentum operator was defined as a matrix. So
Correct.
technically you multiply 2 matrices here, right?
Correct.
So your Hamiltonian is defined as a matrix in this case.
Yes.
So what will pop up if you visualize this POP, P operator?
What you will get is you will get a sinusoidal wave that will show.
No.
He's asking about operator before you apply it to the wave function. Just operator by itself.
Unfortunately, I can get back to you on that.
Just try. Like how to visualize a matrix and how would this matrix look like. Other speakers may try to address this question as well. We can make something more interesting than class, just set up a hunt. You have a lot of paper too.
That's a good idea.
Can you go back to matrix with P operator? Okay, so on the right lower corner, there is a square matrix.
Yes.
Which is your Px or POP operator. If you make a mesh of it, comment in MATLAB, what will come up? How does this matrix will look?
It'll look something like this.
No, can you please show like Michael was doing by hand waving, visualizing like how
Do something.
No, no. Which elements of the matrix you see here?
See the momentum.
Zeros and ones.
Yes.
So can you show 0? Yes. Can you show 1? And going from 0 to 1 and then back to 0. Yes.
Okay.
Okay. Square matrix of
Yes.
Okay. Good. More questions to build? If no, then thank you once again. Next presenter is Kailyn Reed, and she will continue the story about operators. So please focus on implementations, not only on theoretical background.
Okay, I'll go faster than the theoretical part. How do I go to the next slide on this thing?
Forward, yeah, here.
This one?
Yeah.
Okay. Okay, I'm going to be continuing what Bill was talking about. So the evolution operator is a linear operator function symbolized by use of t sub s is what I used for this presentation. Two variables t and s that satisfies the three following properties. These three properties, which will be explained in the later slides. Okay, the first property is a unitary operators. So in regular 3D space, there are operators that alter the ordinary vectors while preserving their lengths. And unitary operators do the same thing, but in nth dimensional complex space. So if you're given an operator like a matrix A, its inverse a to the -1 is such that if you multiply the two together, it should be the identity matrix squared. An operator is unitary if its inverse is equal to its Hermitian conjugate, so that u to the -1 is equal to u. Therefore, it would also be equal to identity. The second property is the fundamental law of composition, or the fundamental composition law, which is shown here. And then this is how we derive it. And then the third property is since the evolution operator uses t sub s and the time-independent Schrödinger equation do the same thing as unitary operators, then use of t sub s must preserve normalization, which proves that the evolution operator is unitary, which is shown here. Next is commutation of operators. So the commutative law typically doesn't apply for most operators, which is shown here. The law is used more to define the quantity called the commutator, which is symbolized here, of A and B operators. So in this order matters. So the commutator of A comma B is symbolized as this, which would be equal to -b comma A, but it's not equal to B comma A. So then if A and B happen to be commutative, then they should equal 0. So since the definite value of an observable A can be assigned to a system only if the system is an eigenstate of the operator A, then we can assign the values of two observables A and B only if the system is in the eigenstate of both A and B operators. So if we suppose the system has a value A sub I for the observable A and B sub j for the observable B, then we get these two equations. So A times the wave function of A sub I and B sub j equals A sub I times the wave function of A sub I times B sub j, and then the same for B. And then if we multiply the first one by the B operator and the second one by the A operator, we get these two equations. And this is showing how to compute commutators. So since The wave function is an eigenfunction, or this is the eigenfunction of the A and B operators.
May I interrupt you?
Yeah.
I think the goal of this presentation is not really give us a theory about what is operator and what is the commutation of operators, but how it is implemented in this specific software. So right now, and you have only 5 minutes, you spent actually half of your time talking about general things which do not really connect it to the topic, to the question which you were assigned to present.
Right.
Sorry for interruption, but honestly, our time is a precious thing.
Yeah.
So I would really appreciate if you skip through this material and go directly to the point how all these things implemented in the MATLAB, and then you can return back and explain what exactly this operation in MATLAB means in terms of general ideas, what is operators.
Okay. Yeah, I can see. So this is the, in MATLAB, this is the visualization of the momentum operator.
Ooh, I protest.
But how
It's
you
a wave-
define
it's
it
a
in
wave
MATLAB
function.
before
It's not-
getting this?
It's not an operator.
Oh.
Operator is a matrix. And this looks like a function.
Yeah.
Try to.
Okay. Okay, sorry. Is this the function we're trying to find?
So from what you were preparing, it looks like a result of commutation.
Yeah.
So can you explain it?
Well, this is the results, like here's a closer view right here of the momentum matrix and the position matrix of the real and imaginary parts. This is the result of the computation of the two.
So it is a matrix that comes from product of two matrices, each
Yeah.
of which is position and momentum operators.
Yes.
So how do you interpret what you see?
That's a good question. This is not a very good picture, but right here it goes down and then up for a little peak right there, which is, I think.
No
Is-
no
no.
relation to this figure.
Okay.
It more relates to what Bill was showing, like 0, 1, and then again 0
0,
on the main diagonal. Can you go back to your slide, a couple of slides back where you define commutation of position and momentum? Stop here, yes.
This one?
Yeah.
Yeah.
So can you relate your last figure with this slide?
Is the peak h bar, negative h bar over I?
But the negative h bar over I is a number, and there you have a matrix.
Right.
So what is the connection between this minus h bar over I and the matrix that you show on the last slide?
Is that the value that this, like the peak goes to?
But what is the connection between number and a matrix? What is the main property of this matrix? What are the blue values away from the main diagonal?
0.
Okay, so it looks like diagonal matrix or something very similar to diagonal.
Yeah.
Okay, can you comment on this?
Not really. I don't know. I got confused. I'm sorry.
Okay, so let me help.
Okay.
So the commutation of position and momentum operators should give the identity matrix multiplied by this constant. And if the position and momentum matrices are implemented in the right way, their numerical commutation should give identity matrix with some non-zero element in the center.
So these would be the non-zero elements.
Yes.
On the center. So then.
And can you return back to your previous slide?
This one?
The last two formulas I don't understand. You have your commutation relationship commutator between x and t equals minus hi acting on psi, and then the next slide psi disappears and you just have minus h over I. I kind of don't understand exactly this means.
If you want to
So-
correct and explain how you plan to correct the equations feel free.
Okay, yeah, I can try. So what I did was, let's see where it is. So here I pulled out the h sub I constants from these two terms, and then these two terms canceled out, and then e dx of x I got to be 1, so it was h bar times I times the wave function. But on the previous side,
No, do not go to previous one. Stay here, otherwise it will be confusing.
Okay.
Let me help, otherwise we will stay here for.
Okay. Do you need this?
No. Do not leave. You
I know,
will answer
I'm just
questions.
moving over to the side.
Okay, so probably you wanted to tell that one is placing artificial wave function after this operator. Okay? So you have wave function here and there. And then you removed it from both left and right side.
Right.
Right? Okay.
Yes. Sorry, that was.
So let's ask questions to Kailyn, and you can go back to the focus of the camera.
Okay.
Questions?
So, but return back to the figure which you were showing many times, this oscillating things. Yeah, so what exactly?
These ones?
This one, yeah. So, because it was like, you're trying to use this as an answer to Dmitri's question, but looks like it was not right. So, can you then explain what exactly it shows?
This is the wave function, and then I think
The black one is a wave function?
yes, the black one is the wave function, and I'm
In coordinate space, like you're showing the distribution over the x. Okay.
yes, and then the red one is the imaginary parts, and the blue one are the real parts.
Of the same wave function.
Yes, I'm pretty sure.
Not wrong.
And then you act, and then what you do with this wave function?
I put these in on accident. It wasn't supposed to be these two screenshots.
But what,
Or you
what
apply your
what does the
commutator.
code? What does the code does to this wave function?
Which
No, this wave function is not related. It seems that it is not related to
it's
the.
yeah, it's not related to this one.
Oh, I see.
Sorry.
More questions? Levi?
So is the black the probability?
Which
Black?
So go back one slide. Is the black line probability
Density.
or density? Okay.
I will help
Probability
you.
density. Because it depends on the coordinate.
So what's the point of the commutation? Why do you do that?
To find the commutator.
Why do you need it? What's the physical meaning behind it?
Good question.
Actually, does commutator has any physical meaning? Or is just mathematical tool?
I think it's just a mathematical tool.
Everyone agrees?
What's the opinion of the person who asked the question?
My opinion.
No.
Yeah.
First was Braden.
I was kind of looking just for the answer. It's kind of the cost to flip the order.
Oh, of X and P?
Yeah.
You
You
want to
get
know
that.
what happens if you do?
Well, I mean,
That
that's the
changes.
answer.
It changes the sign to that, right? Yeah. Is that what you were asking?
What if you use different commutators and they will commute and you're getting 0 instead of some number? Then what does it tell you?
I think it tells you that you would get the identity matrix, wouldn't you?
Or zero matrix.
Or zero matrix.
So then
So-
what physical meaning of this?
Um,
Does it relate to the Heisenberg uncertainty principle somehow?
Oh, I
If you
did.
have heard about it.
I saw that in my research, but I
Okay.
didn't put it in my presentation.
So then put everything together and answer the question.
I don't remember. I'm sorry. I just.
But what is a Heisenberg uncertainty principle tells in general?
I don't remember.
Anyone remembers? Why it calls uncertainty principle? And by the way, I think you were even talking in general chemistry about these things. Supposed to.
Because you don't know exactly where, you only know the position or the momentum, not either.
Right. Right. So actually, if you have your commutators given a number, something, rather than 0, it means you cannot know with 100% accuracy either x or momentum, either coordinate or the momentum, right? So you can give only probability of being at this specific coordinate with some probability, or being with this specific velocity. And if you know that velocity is exactly 2.1 meter per second for your particle, for your wave function, then what you can say about how accurately then you can know the coordinate?
Okay.
The question is, how accurate then? If you know for sure what is your momentum, then what would be the arrow in the coordinate?
Well,
Or you can say certainty in the coordinate.
so you wouldn't know the position.
You don't know at all, right?
Right.
It would be very broad wave packet with all possible coordinates. So in other words, you don't know where exactly your wave would be, or particle would be.
Okay.
Okay, let's thank Kailyn for being brave and making an effort. So next presenter is Alex Hart, who was so humble that he called his talk the best one. And let's check if it will be true. While he's preparing, let me attract your attention to the last slide of the printout. So it is a homework for Monday. So please try to write a sentence in reply to each of the questions, and it will be based on what is presented today. So basically, attendees of the course are teaching, and attendees of the course are answering how they perceive this information. So, the best one.
Maybe. So I'm going to be talking about operators and finite differences. We've already touched on this twice, the initial conditions and how it'll affect the wave packet, and the three different types of ways you can calculate the Hamiltonian and momentum in the code. So the first one, Bill touched on this a lot actually. So when he was saying his big matrix with ones and negative ones and a bunch of zeros, this is what this line of code defines. And I'll go more into the theory and where these relate to each other. But then using this matrix that has negative ones on the diagonal and ones on the upper diagonal, you're going to go down to calculate momentum using the x in like super small chunks of little steps of x and little steps of time. And then if you come down here, this is a second one, and I believe it is just to calculate in 3D space instead of just 2D space. So that's the code. This is the definition of a derivative. I'm sure everyone sees that and loves it. But in order to apply it to ours, we need to use the wave function instead of the wave function is the function. And to get the delta x, when we add the small little step, it would just be delta x minus the original wave function at that position all over the delta x. And that's how it would plug into that.
Should it be x plus delta x?
Right. Oh, yeah, I just assumed that was what delta x was. Sorry. And then, so if you take the first step, you have the initial, which is the wave function at 0.0, and then adding a delta x on will give you delta x. So then, oh shoot, I did not plug that in. But for the second step, you'd have the wave function of 2 delta x minus delta x, and then you minus the wave function of delta x, because that would be the first step, and it's still all over delta x, and you continue on. And in this code, I'll show you a little bit later, but it's defined 200 different points. So this is in class, we kind of went over this in the lab. This is just a refresher for everyone. We go down to 200 points in this code. And then here's for 3 steps, because PowerPoint doesn't let you do more than a 3x3 matrix. So this is what it would look like. And normally we go down 200 points, and then at the very end you have the cyclic boundary condition. There's a reason for that, but I don't actually remember why. Oh, I do remember why. Because when you get to the very end, you're going to come to the end of your box or however far you're measuring, and it's going to come back out the other side just because of the way things work.
So then what is the dimension for this matrix would be?
So in the code, the dimension should be 200 by 200. I can't represent that here, obviously.
You cannot take 300 by 300?
Oh, you can make it whatever you want to make it. The more you make it, the more accurate you get, but the longer it'll take to compute. So in the code, we use 200 because it takes about the right amount of time with at least a decent amount of accuracy.
It actually just defines your kind of interval or from 0 to wherever your maximum with whatever intervals for your delta x is chosen, right?
Yes. So if you do this and you have the coefficients in front, you are going to get I times h bar times the derivative of the wave function represented in a discrete form. Now we move on to the next topic, which is the wave function and the initial conditions. So this is, like Kailyn said before, the orange red thing is the imaginary wave function, while the blue is the real part of the wave function. This is, like she also said, this is the distribution or the density of the wave function at certain positions. It's not labeled, so it's supposed to be at certain positions. But why that matters is this is the original wave function, just plotted over here so you can see it better. But if you change the initial momentum, the amount of times that this will oscillate through here increases. And that'll be shown, I believe, in the later slide. I hope I put that in there. I did not.
So just a second. You're saying that what you have on the right, this is your initial wave function?
That is what we
and what you have on the left or middle, this is after operating.
After increasing
of your momentum operator on this initial wave function, right?
No, I was saying that this is just after you increase the initial velocity. This is the increased initial velocity, so there's more oscillations through the imaginary and real wave.
So you're comparing two initial conditions.
Two initial
and you
conditions.
just put them in the same figure for better comparison.
Yes.
And you artificially offset them by position.
Yes.
Okay.
And so, like I had said before, we got to it finally. Endpoints equals 200. This is referenced through the code many times. It just gives 200 by 200 matrices for the most part. And then right here is your initial momentum or velocity in atomic units. So if I go back here, this one is 0.425 like it shows in the code, and this one is 3 times that amount. So as you can see, it does give a rapid increase in oscillations. And in order to offset it, I just changed this to 80. That seemed to at least keep it on the page while offsetting it enough. And then the rest of this is some of the initial conditions that you can set for your wave function if you would like to change those. This is the actual wave function equation. Dimitri actually highlighted stuff for me after I sent him the thing. So this is the plane wave, but it also is where you can change, or it also is where you factor in the initial velocity. And then over here is the Gaussian distribution. So it actually shows the original wave function, like how you would get the Gaussian distribution. And all of these parts, like where it says norm 2 and norm 1, is just the normalization coefficients for the wave function.
So technically, these two wave functions which we are showing before, it's just some kind of what is implemented inside this formula.
So the wave
like
function.
special two instead of how many of them are involved there.
So this was just 3 times, and then this wave function uses those values. It's just later on in the code, whereas this is the beginning. So going back to this one, this is 3 times the original P naught, and then it just goes into this equation and is going to give a nice looking thing. And then the last thing I got for you guys is the alternative methods to compute quantum dynamics. Most of these are just changing how you would define the momentum in Hamiltonian. So Bill already touched on this. This is Ham. The Hamiltonians are called Ham, and the P and the momentums are usually have the word P, Px, P. So originally it's just defined as h bar times k. I thought k was defined earlier, and I thought I had it in here, but I obviously didn't. So what this does give is a vector, because it's not actually a matrix. So in order to get it into a nice matrix for us, you have to diagonalize it, which just puts all the vector forms down the diagonal.
Just to interrupt you, I think you can probably, it also helps you kind of to focus a little bit more. So the first way how you're representing your momentum operator, and same as was the first for the first presenter, it was in an X space, right? You present your momentum through the coordinate, just kind of using the derivative d over dx, wherever the coefficient in front by the definition, and then just kind of finding the way how to put it in a matrix form, because this is a form which really the MATLAB is easy to work on rather than differential equations. But now it looks like you're trying to go to a K space, the momentum space, where the operator, where the K is just eigenvalues of the momentum operator.
Yes.
And that's you assume that in a K space, the representation of your momentum operator would be much easier mathematically rather than an X space, because as X coordinate is not the eigenvalue of momentum.
Yeah,
So this is kind of the difference between these two approaches. You just approach the same kind of idea of momentum, but presenting it in a different space through the k vectors in a momentum space.
yes.
And supposing that this probably would be simply mathematically,
Yes.
which you can again maybe check with your MATLAB and see whether it's really true or not.
Yeah, that's exactly correct. And then also touching on this operator right here is the evolution operator in the form of k-space as well, so in the form of momentum space. So the second method is using it. Shoot, how did I talk about this? I don't remember. This is really bad. But it just uses the original one in k-space. It helps convert it over into something more useful for us.
So what is W? Is it
You wanted to tell Fourier transform?
Fourier
No,
transform? Yeah?
Thank you. That is the Fourier transform. It's using the Fourier transform and the original P operator that we had defined in the last slide. And then using the PX, the new way to define it, we defined a new Hamiltonian. And it's the momentum squared over 2 times the mass plus the diagonal of the I know what I'm thinking of.
It's the same W as in the top, right?
No, that's a V, so it's the potential energy. That's what I'm trying to think of. I can't think of the word for it. And then if you come down again, keep using the new variables. We define a new way for the evolution operator. So then if you keep coming down, you will see new equations for the next wave packet for using the alternative methods of calculating it. And then the final way was what I had shown originally, using the matrices with the cyclic conditions of the diagonals with the ones and negative ones, and then going through and calculating it out. This is the way that we used in the lab, I believe, once we got all the way through, because this is the easiest way for the computer to calculate. I believe that's it.
Okay, we thank Alex. There could be more questions. Questions? And if you do not know which questions to ask, just look for questions for everyone and check if you want to challenge Alex with one of them. Stay.
Oh, sorry, I didn't see your hand go up. I just put it.
So are there any negative effects of these cyclic boundary conditions, or why do you use them?
We use it because it is impossible to finish that matrix in the space that we're defining right now. So we use them because it is a good way of just defining it for the computer to have a nice way to go through, I believe. Dimitri might object to what I just said.
I didn't hear.
So what if it's small?
Then we would have a very inaccurate thing, a very inaccurate wave function, because we don't have enough points in order to get that wave function to go all the way to the end of the space we had defined, because you need enough of that for the cyclic boundary conditions to come back in. Because if you have too small of stuff, you're not going to get enough points to define a complete wave function, but if you have enough points, the cyclic boundary condition is a negligible difference.
So if you return to the slide where you start with alternative definition of operators, and you start with momentum again with this W.
With the W, yes.
So am I right? So your pop is defined here in a previous slide as h bar k, whereas k is just momentum,
yes.
right? So means you first present operator of momentum in a k space. Then the question is why you need to apply the Fourier transform.
Why you need, so you
What
actually,
exactly this operation is given to you?
so I don't remember what the actual word for it is, but when you, not commutate, but when you multiply it by the Fourier transform, you're having the actual operator in the middle, and you're Fourier transforming the px into a different one. So when you do it like this, this is the, what's this p star, right? What's the star called? Conjugate, thank you. This is you're multiplying it by the conjugate and then dividing it by the amount of points so that you actually get the px operator.
When we apply what's the reason to apply the Fourier transform in general? Not really in specific this case, but in general. This is very
Nicer
useful technique in
graphically.
spectroscopy, by the way. This is what spectroscopists do all the time.
I think it's just nicer graphically, as far as I know. I don't actually know the answer. To
No,
it.
this is operation which helps you to go from X space to K space.
Oh.
So technically what you're doing here, you define your operator in a K space. But then it's not very convenient to work in a K space probably. And you kind of doing this alternative approach, returning it back to the X space. But that's why it's an alternative. First, you define your operator in an X space initially through this matrix where you, in your beginning of your presentation and very first presentation was presented through something divided by delta X, right? Psi at X, delta X, delta
Okay.
X. Here, alternative means that you define your operator in a K space, which is very easy to define. But then you do Fourier transform, and of course, mathematically, it's also taking some time, and that's why both methods probably not give you pretty much the same mathematical time consuming. But it's different in a way that now you get in operating in X space, but through the different way, putting it first in a K and then converting it through the Fourier transform to the back to X. Am I right? Is it what this is kind of doing?
Yeah, you guys are right. Thank you.
So let's let Alex to return to his seat. And, it looks like Ben wants to present next presentation. So, the presentation by Ben will address some of the questions that were asked to previous speakers, especially the question by Braden about size, amount of grid points.
It's also hopefully going to be a lot shorter. So I'm Ben, and I'm here to talk about, well, the main topic is going to be talking a little bit about discrete representation of wave functions. This is where we choose a set of values to perform the calculations at, preferably evenly spaced over the desired space. And this is used as opposed to continuous representations because it's easier on the computer. So we have some examples. So here, this is an example of the probability distribution of position through time with that's a really tiny laser, with the brighter points being more likely, like where the wave function is. So this is with 200 grid points, 100 grid points. It starts to look a bit choppy.
Can I interrupt and ask for which potential?
Potential?
Yes, because the result of these diagrams will drastically depend on the potentials, and it doesn't look like straightforward motion. It reflects somewhere.
Yeah, well, the thing about that is I didn't actually realize it until I set this all up, that the actual potential well actually changed as I changed the number of grid points. And
So they're connected.
yeah.
But is it like barrier or well or just generally?
Well,
Step function.
yeah, the way that it's set up is it's a barrier.
Okay, good.
So-
Enough.
So this is with 50 grid points. Notice that the slope of the line is a bit different. So, and then 20 grid points, it looks unrecognizable. And I think something went amiss with the code with the 20 grid points. So 720 time steps at point with one, each time step being 0.1, and then cut that in half, half again. The dynamics actually stay the same. As you can see, it just gets lower resolution. And so the code has no problem dealing with lower amounts of time steps. So normalization of the discrete wave functions. This is what the initial wave function looks like in the code. This is it written out. So we have the localized function there. I called it the evolution operator, but I don't think it's actually the evolution operator. It's the implementation of momentum into the wave. So this is the normalization from the standard wave function. And then we have to normalize it again. We have to normalize it again because not actually what this function looks like, but we take this function and we turn it into a bunch of rectangles of width dx. And so in order to actually get an area to normalize, we need to multiply it by dx. And we end up using the square root of dx because in order to get the probability, or in order to normalize it, we take the square of the function. So size versus time. So you'll find that in this, the code erroneously finds the wave function wraps around the simulation space, which is, you know, it's quantum physics, anything can happen, but I don't think that that can happen. And so there's two solutions. We can shorten the time of the simulation. The pro of that is it's straightforward to implement. The code really likes you changing the amount of time that the simulation goes, but the cons is that it limits the dynamic part of the dynamics. You know, it's dynamics. We want to see how it evolves in time. And if we cut short the time, then what's the point of doing dynamics? Or we can extend the space. We can extend the box. The pros is that it allows for extended dynamics, but the cons is that the code doesn't really like you doing that. It does really funky things with where the barrier is and the widths of the barrier. And so you would need to alter the code a bit more in order to do that. So, that's it.
Okay, let's thank Ben. Any questions you wanted to offer him to enjoy? Jacob?
I have a comment on your first, no, I mean here in this slide. Why you think that code erroneously write on the other side?
Well, because the wave function is going from this side, hits the barrier, and then goes over there. And we are simulating a wave function in free space hitting a barrier. And so it wrapping around the other side doesn't really make sense.
When does it wrap around the other side?
It wraps around the other side as it hits the edge of the simulation space.
So what does it mean? Like code is calculating as a periodically, it's not just erroneous
It goes kind of in a circle, right?
in a circle.
Yeah. Well, my point was it was erroneous compared to what would actually happen in.
But do you see the solution for this?
Or
Or at least limit, decrease the effect somehow?
well, other than these two,
Two? You have too many points here for me.
the two solutions would be to shorten the simulation time or to extend the simulation space.
Could that, are you talking about the lines, the interference pattern? Because couldn't that be due to your barrier?
Well,
Yeah, in other words, could it depend on a barrier as well, right?
Yeah, because if it tunnels into the barrier, it's not like a ball hitting a wall and then coming straight back. It's like a million balls hitting the wall and then watching them return back. So some of that could be due to the barrier.
I suppose that's true. I didn't really I don't really expect that based off of what I saw, but maybe I just don't know enough about how it would actually act.
So you can see in the plot that like 95% of it goes through the barrier, right? But then maybe 5% of it gets reflected in the light blue lines. And then when they hit each other in the boundary conditions, that's what causes the interference.
Well, maybe I could have made a movie of the dynamics, but what I ended up seeing is that the wave function went through space, hit the barrier, and then kind of went through the barrier, and then some of it started reappearing on the other side, almost like it wrapped around. So.
And if you look around 100 in your, what's your x-axis? Position, you can already see destructive and constructive interference due to the barrier right away.
Okay. Your answer is okay. So, more questions to Ben? If not, then thank him once again. So, Dylan? Main goal of quantum theory is to predict what comes out of an instrument, to predict the values of observables. And Dylan will help us on this pathway.
Alright, so we're dealing with some observables. So this is, we're working on the accumulation of expectation values. So to find the expectation values, you take position, to find the expectation values of position, you multiply it by the probability throughout the x-axis, which was shown in the line 208. Then you take this and you use the summation, all these values, and you will obtain one number, and then you gotta keep looping it. That's why you have the average, because you keep looping it, and then you will actually be able to show how the graph moves throughout. So you keep obtaining a new value, and then over the time, and then it'll show you your function. So that's what's showed over on here on the right. So then by in MATLAB plotting the AVGS3, then that would show your function. And so the purpose of showing the accumulation expectation value is to predict the future. And then by taking the average of all the values, your expectation values are obtained. Moving on, just saving some numerical data in Excel. Basically, you just go into your Excel sheet and you hit your save as, and then you just name it whatever you want to, and then make sure you save it in MATLAB, and then it'll actually pop up in MATLAB as shown up here. Just as the numbers, I just did a data set in Excel, saved it over there, and then I just, in MATLAB, writing the data set, and then that equals the XLS read, and then your Excel sheet, and it just was able to pull it over. And then here's just some kind of loading and saving, working with the MATLAB. And so hitting the save data set actually saved everything that all my variables. I just had a bunch of matrices, and then I had my data set, which was over here. And then just storing it, and then be able to you could hit clear all, and then being able to load your data set again, and then just be able so you can use your matrices or anything, any data that you need to. And then so there's just another way of displaying your data sets and everything. So here's just, you can see all my variables on the right, And then it just shows the size of the matrix and everything else, just if you need to use your variables. Okay, so like finding your expectation of values of position, you do your set the summation of probability times your entire x range, and then which is also shown as your wave function star times your x times your wave function again. And this can only be done with a diagonal matrix. And then for momentum, find the expectation values for momentum. You have to do row by column matrix application. So here's your wave function star, and so that's your wave function at a given time. And then that your P of x is actually your matrix. And then wave function n is just your original wave function. And then this only generates one number. And then by taking the average of that number, and it'll just keep producing new numbers, and then plotting it, and then it shows momentum.
Not average, accumulating.
What's that?
Not average, but accumulating.
Yeah, accumulating. Yeah, yeah. So then this helps predict the future of the momentum curve.
Okay, let's thank Dylan for predicting the future of the momentum. Oh, there could be some questions. Can you tell what your predicted future of the momentum shows? How to interpret it?
So it's just it's correlated with your position graph. I know that. I just know as you're speeding up in position.
Does momentum change? Oh, speeding of position.
Yeah, speeding of the position, and then it affects the momentum graph. Because your momentum starts constant, but then it decreases.
So when momentum decreases of any object?
When the position is
slowing down.
Yeah, slowing down.
But in real life, when a car stops,
Yeah.
when it bumps into the wall, right?
Yep.
So it probably there is some barrier.
Yeah. So that's when it's bouncing off
Okay.
the box.
More questions to Dylan? If not, then thank you once again. And the next presenter is Gage Rieger, who will tell an important story about the uncertainty principles.
Okay, so I'm just kind of building off of that last one where I'm going over the uncertainties of those position and momentum values. Now the expectation value of the position, the distribution is kind of like that. It should be about right in the middle. Let's have it kind of, the equation kind of go for the variances. Let's say I'm Gage, doesn't it? It's represented by that. I creatively did not think to put the MATLAB code for that in there, because that would be more, this would be more palatable. As the distribution widens out, the uncertainty kind of increases. So, thinner one, I'm not going to say it's necessarily certain, but it's a lot more certain. And then the variance value that is showing here is kind of the representation of that. So as we start out, it's not so bad, but then it's kind of compounding on itself. As we reach a certain point here, it just decides to shoot up, and we really lose any information about that, part of which is due to the bouncing off that was mentioned in earlier presentations. And here we have momentum. Follows much of the same principles. The drop here is about when it hits the barrier, so that's when we kind of better idea of where it is, and then it shoots back up, back down again afterwards. And we have the product of the two, which must always be at least greater than h bar over 2. So if we know everything about one of them, we know nothing about the other. So at this point where the momentum was the smallest in the just momentum, we also have a pretty good idea where the we have a low uncertainty there as well as on the other side when it drops. Highest in the middle, where the momentum uncertainty was the highest. We can kind of see how as the position uncertainty is increasing, we also have a lot higher numbers there, so kind of really screwing things up. And that's all I really
Okay,
have.
let's Gage. Anyone wants to challenge uncertainty principle?
Can it be uncertain? Can it be equal to h bar over 2? Or is it always supposed to be higher than h bar over 2?
I saw greater than or equal to and just greater than. I wasn't really sure which one to put, so I just put greater than. So, yes, it could be equal to it.
So, you have the definition of standard deviation on a couple slides.
Yeah.
Is that the standard deviation, or is that something related but a little different?
Are you asking for the equation, or would I have the graph?
The equation, yeah. Because the standard deviation, that's kind of measuring like a range in a certain value, so it should have the same units as the value.
Yeah, I think I have just the equation for the standard deviation, so the graph should be variance. Gets over that bit.
I think what I'm getting at is, can you just go to like the second slide of the presentation? Like, maybe I'm wrong, but it looks like that second equation, you should take the square root of the right side.
Yeah, I have a point there.
If you want to call it standard deviation.
Isn't that what sigma is?
Yeah.
Well, author has a freedom to call it any.
Okay.
Anyway.
I prefer to call it what it's supposed to be. If I'm wrong, I'm wrong.
So is there any function that is like defined to have the lowest variance or dispersion?
I'm sure there is, but that wasn't the code that we were given, so.
Remember, this question is very appropriate, but it is too early.
Okay, sorry.
Come in a month and ask it again.
Okay, I can't immediately answer it then.
More questions to Gage? If not, thank you once again. And Joseph Dahlgren will help us to deal with a multitude of data and results that this code can generate, and show how to get something useful out of it in practical sense.
So this is dealing with visualization. So visualizing the real and imaginary wave parts of the packet, or the wave packet. So here the blue is the real part of the wave packet, and the red is the imaginary part. This is with the initial conditions. So this is the distribution of the wave packet over the two. What the black line is. And then this is kind of what Alex was showing, whereas if you change the momentum, you get more fringes. So as the initial momentum is increased, you get more fringes. It bounces up and down, has more peaks and valleys. So this is where it's 3 times the momentum, and that's the original. So then this is visualizing the potential and probability distribution. So on this, the blue is the potential and red is the probability, whereas this is a lower probability than the one on the right here. So then if you increase the energy, this is where the original was. If you increase the energy, the probability is higher, and this is still the potential. So if the red line goes above the blue line, then it doesn't have enough like activation energy to get through. So like if you have a chemical reaction, it won't go if there's not enough activation energy. And then this is just when we ran the code, where the black line is where it is, like where it should be, the actual thing. And then this
It should be in absence of potential.
Yeah. Yep. So if you had more data points, these lines would be closer to the black line. It's just the code wasn't is made to go quicker instead of going on forever. But the more data points you have, the more accurate that can go. So as kind of Alex explained, there's 3 different methods that you can use to determine. They differ by how implementation of momentum is pretty much, and then we showed the different implementations earlier, and that's about it.
Okay, let's thank Joey. Questions? Dillan?
So on one of your slides,
Yep.
This one and I think the previous one.
Yep.
If your barrier compared to your momentum goes to infinity, will you see any tunneling? Because like the one on the left, you see probability within the barrier.
Yep.
So if the barrier goes to infinity compared to your momentum or energy,
Yeah.
would you see any tunneling? Or would it hit it and then bounce straight off?
I think if it went to infinity, you won't see any tunneling.
Okay.
That's just, I mean, from what I've seen.
Satisfied? Okay, more questions? If no, let's thank Joey once again. And Michael Odegaard will correct any errors made by Joey if there were any. If there were no errors, he will just confirm that it was correct. And then he will probably summarize part of the month ago talk by Bill, telling theory how to make movies, which later will be shown and implemented in the last but not least talk by Syed.
Okay, I'm just gonna kind of continue on. Mine's more about like the software than the chemistry stuff. Okay, so a plot, an observable. You do the independent variable, which was prime, and then the barrier, which is the V. And then to do multiple, you do, this is the previous one, you do another independent and then another dependent. Pretty basic stuff. And then to put more than one plot in a figure, you do subplots. And then like how many you want, and then see this is the first one, and the code for it, and the second one, the code for it. Third one is further down. Okay, so then this is the part of the code. I kind of struggled with the movie thing. I got thrown a little late, but this is the code for the visuals for the movie. And then to export them to YouTube, you do this, the right video via frame. I couldn't get it to work. That's why I did sealed bell slide. I couldn't figure out how to convert it to like the .avi,
But can you briefly share your vision of what these boxes mean? What is the functional reason of each of the 4 boxes?
These 4? Okay.
And skip the first one, go on with the last 3.
Okay, so that's just converting it to the .avi.
No, it's just opening stream to save.
Oh, okay, yeah. So it's opening that up.
Next line.
Is running it.
Next box. Yeah.
So that's just running it with how many frames per second.
Okay, so catching frame.
Yeah, catching it, and the last one's like stopping it and saving it.
Okay, very good. Let's thank Michael. Any questions? If not, let's thank him once again. And last but not least, Isaiah. So his talk is special. He is a pioneer of the application of this code to multiple different applications. As you know from how code is arranged, you can change the potential and apply this code to different problems that one cannot or has difficulties to solve by pen and paper. And
talking me up a lot. All right, my name is Isaiah. I have the applications of the Wavepacket code. So first, the challenge was to put the Wavepacket within a box. So if the box is infinite, it's almost like the Wavepacket is in free space. It'll propagate on through time. In the case of a finite box, the waves will oscillate back and forth, bouncing off the edge of the box. And then the wave will not escape the box unless the potential energy is high enough, or the activation energy is high enough to escape the box. There should be a video here. Then some of the biggest troubles I had when creating the videos themselves is saving them under the right format, and then also using the same code to make multiple videos. You have to save each different video or version of the code as a different name that you would want to keep. Otherwise, you're just going to keep going back and forth and trying to make sure you keep everything straight, and things just get really confusing at that point when you're going through hundreds of lines of code. All right. The next example I had was a barrier. You can see I have the position versus time graph here. And then it has this characteristic break here. You can tell there's a barrier that the wave is hitting. A similar example, like Dimitri told us in lab, the wave will run and hit the barrier, and then it'll come back and appear on the other side going through. Yeah, and I also have another video of that as well. So you can imagine we have many barriers all the way down, all along. And then even if it is hitting this barrier, it tunnels through, or it should here pretty soon. And you can see some of the wave appearing on the other side. That's when it's reappearing from the back end. And then the harmonic oscillator. Again, I have position versus time graph. Another characteristic of this, as you can see the probability here. Going through the yellow spots are the highest probabilities there, and it makes this sine or cosine pattern. I also have a video of that here. It'll oscillate between parabola, and then the only issue I had with this here is the time steps are off between the waves, but other than that, it does show a very good representation of harmonic oscillator. So if this goes on long enough, the distance between our waves will increase, which really isn't supposed to happen. But it's not the worst example.
So what are the two waves here?
Pardon me?
What are the two waves here? What does each one mean?
I'm not 100% sure.
how does it relate to explanation by Bill and Alex and others by 3 different methods?
The probability.
Different ways of defining momentum operator.
Not 100% sure.
Is it last slide?
Yeah, that's the last slide.
Okay, let's thank you, Simon. Any questions? Please.
So on the finite potential well, the first video you showed.
Yep.
So you started it. Did you start it with some initial momentum at all, or did you just let it go?
I believe we did start it with some initial momentum.
Is there a way you could get it to go with no initial momentum and just have it stay fixed in space?
I'm sure if we set the momentum to 0, we could.
But what is the main reason of this oscillations?
It's reflecting off the other sides of the box.
And that initial state is not an eigenstate of the system. You wanted to say, right?
Yep. So
okay. More questions? If not, let's thank you, once again. So many thanks for all presenters for hard work to prepare and stand the questions. There will be a little analysis of performance, especially in answering questions and then assigning grades, but generally everyone progresses well in courses. If you were feeling difficulties in answering questions, it's kind of a little navigator where to improve and put additional efforts. Look not only on your success or unsuccess, but also on others, right? And we are a little more squeezed in schedule in order to have the end of semester easier. So please try to answer questions at the last page of this slide by Monday in form of emails or Microsoft Word. Do not write by hand. Okay, done. Many thanks. Congratulations with successful completion. Meeting is done. Have a nice weekend.